throughout India. So over to you now, Dinesh, to give us a look at dewatering.
Thanks. Thank you, Mark, for such a nice introduction. And I hope the slides is now visible on the screens for the audience and panelists. Uh,
And
just wanted to add and introduce myself. Uh, Good afternoon, ladies and gentlemen. I'm Dinesh Gihani, and I'm Regional Product Sales Manager with GIA Group as a part of business unit separation. Uh, and just to introduce, GIA is one of the largest system and solutions provider, making contributions to sustainable future and through its solutions and services, and working with engineering for a better world as our driving and energizing principle. Uh, on Since almost 1893, we have been building centrifuges, and which we combine with high separation efficiencies, clarifying efficiencies, and throughput capacities to provide our customers maximum savings in terms of energy, water, and disposable cost. Uh, as I move forward, I would like to connect some dots, and very interesting presentations by Miguel, Chris Piot, and even for the audience who would have attended the last session of yesterday's session about recycle and reuse, and since we are continuing, and if you recall, uh, um, Anil from Royal Huskening and Mr. Salvi from MCGM did talk about a lot on water reuse. But as we are moving towards in these sessions, you would have noticed that we are talking about the another part of the reuse and recycle, which is the solids or biosolids, whether it is bloom for as a manure as a class A solids, whether we talk about Downer in Australia, talking about gasification, making biochar of it, of the solids, or we are talking about Nereda and Royal Huskening trying to extract biopolymer and using them as one of the ingredients in ceramic, textile, and wood processing. Uh, but I would like to give you an overview that we start with where is really dewatering or thickening used. Uh, what are the drivers or factors for it? We should understand. The other part we would move into what are the technologies are there, and what are the drivers to select those technologies, and where do we move forward from here, and where does the dewatering plays a pivot role in making this reuse and recycle an efficient value chain. Moving further, uh, once we move to sludge dewatering and thickening, so where is it, sludge dewatering and thickening? If you see, this is a standard schematics of a wastewater treatment plant. It does look like a very simple schematics, but if we go a bit deeper into it, you would see the first part is water management, and the water from this part was, we were talking about recycle and reuse yesterday. When we move to the second part, the byproduct of the water treatment is the solids. The biosolids have to come out, and this is the byproduct. And I use the word byproduct because, as Chris and Miguel talked about, uh, the solids are not liabilities. They are we are the approach is changing, that they are becoming an asset, and that is why I use the word byproduct here. So it is the byproduct of water management process. And what happens here? It is, if you see, a bit of sludge management happens here. Either you would thicken it a bit more, or use pre-treatment technologies like THP to improve the digestion, or make class A solids so that they further can be used into another value chain of reuse and recycle. And that's what completes the picture. But and if you see the dots, that dewatering, the right selection of the dewatering equipment is the key to see whether my next process of reuse or recycle is going to be effective or not. If the dewatering is not efficient, then the bloom would not be as dry as possible, which is required. Or your energy for incineration in the next process would be very high. So let's move further and try to understand what does what as a buyer, as a user of a dewatering equipment one should look for. What are the critical requirements? We want dewaterability to the maximum, driest of the solid, no doubt about it. Separation efficiency. But I would use a different word, is what is the retreatment cost of the return solids of a dewatering equipment? You get 100 kgs into a dewatering equipment, 50 kgs go out, become solids, very good. The rest of the 50% goes back into the system. What is the retreatment cost of those solids? This we need to understand. The other part is consistent performance. Yes, this is the pre-need of any equipment. Moving on to the last part, which is utility consumption. And the moment we say utility consumption, we have a very emotional connect with energy consumption. But we should look at it in a very holistic manner. It's not only energy, it's about, again, the treatment cost, wash water cost, uh, space cost, operation cost, and all the utilities, including the chemical and polymer cost. How do we achieve dewaterability to the maximum? We need a mechanical separation force, we need torque, we need hydrostatic pressures. Retreatment of the solids also depend upon separation force and real-time solid conveyance adjustment, plus avoidance of fouling of the system. Because if the system has a fouling, then this return solids would become very high. Consistent performance has to happen with monitor and manage, which means if we don't monitor what we are doing, it's difficult to manage. And for utility consumption, it has to be looked on a holistic model. Moving further, what exactly is mechanical dewatering? What is the basics of the dewatering? What do we separate? We separate water out of the solids, which are bonded loosely or free water. So if you see, this is the microscopic view of the structure of a biosolids with water. And what you see A is the free water. B, if you see, is the internal water, which is bounded in the interstitials inside the flocks and particles, or maybe uh, having bonded by capillary forces. C is the surface water, which is bound on the surface of the particles and physically and chemically by chemically, physically or chemically adhesive forces. And when we talk about the D, D is the chemical bounded water with high binding energy or very strong bonds like gels. And this kind of destruction of the bonds require a thermodynamic process, an exothermic process, adding energy to it. But as we are understanding uh, what do we separate? So we do separate any mechanical dewatering. We talk about separation of the free water. The other part is trying to understand that when we set dewaterability to the maximum, what is the key point on which dewaterability is dependent? What is the maximum value? And what you see is the surface water can be removed more from the inorganic content. And that is why this we run this test. And a few of the audience who would have attended the master class by Dr. Julia Kopp, she did also talk about the similar kind of model, which is we are talking about the bigger the ash, higher the ash content or inorganic content, the greater is the possibility to dewater the water, and greater is the possibility to take out the free water. So there is, when we talk about dewaterability up to the max, there is a way to understand, to find out that what would be the maximum dewaterability, and now which of the technologies would reach closer to that, and at an optimum way of what is the optimum way of doing it. Now, if you look at this slide, you would find on the left side, you would find centrifugation, and on the right side, you would find filtration. Primarily, there are only two basic technologies of mechanical dewatering: centrifugation and filtration. When we talk about filtration, there is if you see on the right side of the screen, uh, there is always a physical barrier which separates the liquid from the solid. In other words, water needs to escape through the holes in a cloth or mesh while solid remains. And all based systems or filtration based dewatering technologies creates a pressure difference over the barrier, over the filter barrier, and thereby pushing the solids onto the filter, whether or to the pores. Means solids try to get through the barrier as well. The art of the filtration, if you see, lies in having the ideal filter pores compared to the sludge flocks to allow enough pressure on the solids without any solids escaping with the water. However, the pore size, if you see, will keep on changing as the fouling occurs. And if you see on the uh, if you see on the left side, this part, the fouling and the blocking starts to happen. And this is where the efficiency of this kind of system starts to deteriorate. Whereas in comparison to a filtration system, any kind of centrifugation system works on the principle that solids are separated from the liquid through the process of sedimentation and compaction, which means centrifugal forces is important. And further, in centrifugation, the water does not need to escape via cloth mesh. It is simply lighter. And if you see, the lower pressure is on this side. And water being lighter than solids, it flows out. As you feed the product into the system, the water will remain on top of the solids, and eventually flowing over from the lower point, which is this point. The solids are squeezed by the centrifugal force while being conveyed by a scroll. And this, if you see, is the broad or basic difference between these two technologies. Moving further, this would in turn would give you a summary of what are the advantages and disadvantages. Without a doubt, one works on a very high performance. There is a possibility of continuous operation 24/7. Yes, disadvantages are there on certain parts. Noise more may need a bit more of specific polymer. Energy consumption may be higher, but as I started with, the fourth point was to look at the holistic distribution of the utility, not only energy. And as we move further now, it is important to understand which are my drivers to select the right technology. And if you look at, there are drivers are usually divided into two parts: capex and opex, operational cost, and how much do I put to bring the equipment on board. They can be a driving factor for two different stakeholders, but if you look at that, they are all these, both of them are driving factors altogether. And if you look at holistically as the total value cycle of a particular equipment. Moving further, what we have seen that usually in case of in a typical scenario, you would see this is the distribution of the operation cost with any kind of dewatering equipment. And if you
This is
see the
Dinesh.
gray portion, which is the highest, yep, which is the disposal cost, and then polymer, water, and solids recirculation is one of the cost. And if you see, energy is a very small cost. Moving further, this would give you a comparison between how these different OPEX factors are standing against each other, against different kind of technology. But this would not give you a complete picture until unless we move into a particular case study. And as when we compared for a 5,300 tons of dry solids per year plant for a dewatering. And this is how different technologies stack up. Going a bit more into the detail, we did a continuous 4.5 hour test with at one of the plants in Netherlands at Hengelo, with supported by Netherlands Water Board in Netherlands, where all the three technologies of different technologies were giving the same kind of sludge. Uh, they were all given time to optimize their equipment, and a continuous 4.5 hours of test. What what we've found out, and if you see, these are the details of it. If you see, in terms of cake dryness, the comparison is clear that one of the technologies, which is centrifuge, stacks very high. Similarly, polymer consumption was the lowest, and if we look at the treatment cost, also was the lowest. When we look at this comparison, which is suspended solids, and if you look at this comparison, you would see that this is with the newest of the belts, or with the filter cloth or mesh. As soon as the fouling happens, the efficiency of it starts to decrease, and that's where what we were talking about in the filtration system, this would start to increase. Whereas in a centrifugation based system, this would remain constant. Another comparison, if you see, when this for this particular test, when it was tested, we were talking about 99%, 99.5% capture rate, and there is a certain polymer consumption against it, and as it goes down, it has a decreasing effect and on the polymer consumption as well, and it may go down to 5 to 8 and 5 to 8 when we are talking about 95% capture rate. And similar, you would see the maximum dewatering or the solid concentration would happen at the a certain polymer load, and it would not increase if you even increase the polymer, and would have certain decrease over a period of when you decrease the polymer loading, because that would not help to attract or bond the smallest of the particle. Moving further, what should we look at? What should we look at, and what if we try and compare everything together? What we see in this presentation today, uh, a system would look like this. Uh, One has to decide his their own driver. If I want highest of the cake, highest of the centrate quality, and I'm ready to put an highest of the flocculation, then I am going to get the highest of the load. But when I'm going to reduce my flocculation, I have to reduce my load. Or if I have a bit less of dryness but a very high centrate quality, so where are my drivers? And this is the next future of it. The drivers need to be known, and we must be able to compare products. And this is what I always think, that we compare business organizations on their profit and loss statement, on their credit ratings by CRISIL, A positive, A negative. We compare countries, economy of the countries on gross domestic product, their sovereign funds, uh, but we do not compare the dewatering equipments. And this is where the key of the future lies. The key of the future lies on the gross dewatering performance efficiency. One has to compare the complete drivers and stack together against each and every technologies to look at which is my best suited against my requirements. And this is where I also look at that, when a scenario is of reuse, recycle, one is already looking at its own driver. When the scenario is of what is my return solids cost, and does my centrate is of more important quality because of my further process for the water reuse or something, that's is already defining the future and drivers of it, and correctly understanding the drivers. So thank you very much. And if you have more queries, I'll be happy to address on that.
Dinesh, thank you very much for that detailed look at dewatering. We do have a number of questions which have come in for you. Unfortunately, we're running quite a little bit over time, so we're going to have to forward those to you by email for you to respond to later. Apologise for that, but we are running over. I'd like to move on now
I would
to.
look forward to that.
Okay, thanks, Dinesh.
Yeah.
I'd
Thank you,
like to
Mark.
move
I
on
would
now.
look forward to that.
Okay, good. I'd like to move on now to our final case study, which is to be presented by Sumit Pawar, who is the Sanitation and Circular Economy Advisor for Waste, based out in Kenya. Waste provides support in designing, executing and managing public-private partnerships in sanitation and solid waste management, and they focus specifically on business development, innovative financing and scaling up. So I'd like to hand over the floor to Sumit.
Yeah. So good morning and good afternoon, everyone. So I'm Sumit Pawar from Waste, and today I'll be talking about circular economy of sanitation as a solution provider to the sanitation, water, and agriculture nexus. So this case study is from the SWIFT program and the Securing Water for Food program as objective of enabling or providing innovative solutions to enable the production of more food production with the use of less water, and also make more water available for the food productions. This program started in 2017, and the founding partners of these programs are USAID, Dutch Ministry of Foreign Affairs, and also the Swedish International Development Corporation Agency. And about Finnish Mondial program, this program aims to scaling up the sanitation services across the 6 countries, which are Uganda, Kenya, Tanzania, Ethiopia, India, and Bangladesh. And the Finnish started in 2009, and it's also funded by the Dutch Ministry of Foreign Affairs. And the founding partners for this Finnish Mondial program are Waste, Aqua for All, MRF Flying Doctors from the Netherlands. And this is also currently ongoing project. So today I'll be sharing a learning from our Nilgiris districts, which is in India. It's a horticulture districts, and the problems they're facing are limited water availability for the farming, let's say 4 to 6 months, and extensive use of chemical fertilizers are reducing the soil fertility, and illegal discharge and dumping of solid and liquid waste are creating environmental pollutions in Nilgiris. Uh, so the diamond model approach was used to establish a local sanitation circular economy for the agriculture. And the diamond model focuses on connecting customers, financiers, government, and the businesses together. And in Nilgiris, the farmer producer companies and the farmer groups were representing the customer side of the diamond, and they're connected to the microfinance institutions, banks, and the Leaf. Leaf is a agriculture supply chain company which provides genetically superior seeds and local handhold support to the farmers, also cold storage and also the market for the crops. And the government was engaged in the demand creation and awareness raising activities at a household level for the source segregation, and also provided the basic infrastructure for the establishment of the resource recovery plants. And resource recovery plants are owned by the local town panchayat, and they're operated by women self-help groups. So resource recovery plants were established for the production of co-compost by utilizing the solid waste and also the fecal sludge. And the direct benefits of the resource recovery plants to the women self-help group members are formalization of women self-help group members and improving their technical capacities, and also the health and safety aspects in terms of operations, and also the increase in income. And direct benefits to the farmers who adopted the co-compost in their agriculture activities are the improving the soil water holding capacity, increase in the crop quality and also yield, and that brings increase in the volume of production, and also the cost saving in terms of reducing the input cost in their agriculture activities. So this diagram represents the process flow at resource recovery parks. So the fecal sludge goes to the vertical flow constructed wetlands for the dewatering, and the further leachate flows to the horizontal flow constructed wetland for the treatment, and the dry fecal sludge from the vertical flow constructed wetland is mixed with the segregated and also the shredded organic waste with a proportion of 4:1. That means 4 is the proportion of organic waste and 1 is the proportion of fecal sludge. And this process can take up to for the production of co-composite can take up to 6 to 7 weeks, and for the non-organic part of the waste, after primary and secondary segregation, it goes to the buyers. This is a like pictorial overview of the resource recovery parks, where we can see the constructed wetlands, the co-compost piles, and also the final product, final co-compost product in the bags for sale. And the last interesting picture about the size of the beetroot before and after application of co-compost. Here I would like to highlight some of the key findings from the SWWW performance evaluation report. So 90% of the farmers were positive on the use of co-compost, and the 10% farmers, they said they will use the co-compost in their next crop cycle. And about 100% of the farmers, those who adopted co-compost, found that the increase in the crop yield for their agriculture production, and about 68% of the farmers reported the change in the water uses, and also the 98% of the farmers also reported that there is increase in the survival rate for the seeds and also for the crops after application of co-compost. And about 60 to 70% of the families, they saw the increase in the net family income after application of co-compost for the longer time. And in last 13 out of 50 farmers saw their individual increase in income with respect to the farming activities. But about 60% of the farmers could not concretely monitor their change in the incomes. Yeah. So this value chain and position diagram represent the financial flows financial flows in our local circular economy model for agriculture. So resource recovery parks receives the finance flows from the town panchayat, national government, fecal sludge tipping fee, also the grants from the sweep and finish projects, and also the sales of the co-compost and recyclables. And in the other hand, farmer producer companies and the farmer groups, they are connected to the microfinance institutions in terms of loans and payback, and also agri-making companies and government agriculture department, and also they are also connected to the resource recovery part for the sales and the sales of the co-compost. And all these activities are initially was under the umbrella of RDO Trust and Waste. It's a copy of lab test report for the co-compost, and it has parameters including but not limited to the organic carbon, nutrients, heavy metals, and also the pathogens. We are testing around 22 parameters on regular basis for over a period of 2 or 3 years. So after having a successful implementation of the SWWW program in Nilgiris, so this innovation has provided a springboard for scaling model not only within India but also internationally. Is being implemented under Finnish Mondial program in Kenya, Uganda, Tanzania, and Bangladesh. And right now we are also conducting further research on the co-compost application by looking at the circular economy, and those are soil and carbon study for the application of co-compost, means soil study of soils before and after application of co-compost with Indian Soil Research Institute, and also the greenhouse gas emission saved by utilizing the landfill waste for the co-composting process, and a carbon sequestration study of the soils and after the co-compost applications, and value addition of co-compost for the tea crops, means developing a specific co-compost product for the specific crop, for example the tea crops in Nilgiris. And also we are looking at the feasibility of getting carbon finance, that is carbon credits, for our upcoming decentralized co-composting projects in our 6 Finnish Mondial countries. So this is a structural overview of Finnish Mondial program. On top we have Finnish Mondial Supervisory Board, and we have Finnish Mondial Management Team, which is divided into the multiple working groups such as financial innovations, monitoring and evaluation, technical working group, fecal sludge management, circular economy working group, and communication and Africa coordination working group. So I belong to the fecal sludge management and circular economy working group, and we actively work with our local partners in our Finnish Mondial countries. That those are Uganda, Kenya, India, Ethiopia, Tanzania, and Bangladesh. And this is the infographics of our Finnish Mondial 2020 and 2025 phase, which is focusing on setting the stage for the scaling, also geographic expansion in 6 Finnish Mondial countries. And some of our ambitions for 2025 are utilizing 40 million in grants to leverage 400 million in sanitation investment alone, and creating 16 million works days in a toilet construction, and reuse and recycle 175,000 tons of fecal sludge, reach out 10 million peoples, and built 2 million safely managed toilets in 6 Finnish Mondial countries. Thank you for your attention, and thanks to Kailas and his team for invitation and arranging such informative session for all of us. Yeah, thank you.
Sumit, thank you very much for that look at the work of waste and the detailed and very valuable programs that you are involved in. We do have several questions which have come in for you. Unfortunately, because we're running so late, we are going to have to forward those to you by email. But thank you very much for a great presentation and for your participation.
Yeah. Thank you, Mark.
Thank you. Thank you. Okay. Going to hand you over in a minute. That's almost all from me. I'm going to hand you over in a minute to the chair of our panel for the panel debate, which is looking at the future of biorefinery. Just before I go, I hope over the last couple of days you've enjoyed the contributions from a number of experts who are prominent at WEX Global. As you've probably seen on the banner behind me, our next event is coming up 28th to 30th of June next year in Valencia, all being well. Of course, we don't really know what's going to happen tomorrow, but let's see what happens next year. The reason that I'm involved in the Innovation Week is that Kailash and I had planned to bring WEX to India this year. Unfortunately, we were unable to do that, but we plan to do that as soon as it's safe to do so. In the meantime, I hope that we will see a number of you come to Valencia in June to actually meet and sit down and exchange opportunities and ideas with a number of the people and others that you've seen today. So anyway, our final panel session, as I said, is looking into the future of biorefineries. We have a stellar panel for you, which includes Bill Barber, who is the technical director of Cambi and a widely published author on this subject. Malcolm Fabier is the COO of Dryler, an innovative company from the USA. Chris Peart is going to come back and join us again from DC Water, and making up the fourth member of the panel will be Pedro Pavão, who's the founder and managing director of P Water. Your panel is going to be chaired by Richard Lancaster, who is the Biosolids director for Atkins Global. He is a senior leader within the profession, has more than 30 years of experience. During that time, he's developed and implemented biosolid strategies, created compelling cases for large capital investment programs, sponsored the delivery of major capital programs, and represents the industry on key biosolids regulatory commissions, setting the path for government policy on the future of sludge. So with that, I'm going to hand you over to Richard, and thank you all for coming today. The floor is all yours, Richard.
Thank you, Mark. Very nice introduction. Appreciate that. Obviously, I started very young, as you can see by my wonderful youthful looks. I just wanted to thank you for the previous session. I thought there was some brilliant presentations, some real thought-provoking stuff, particularly Frank's, who's desperately trying to put me out of work, and I will therefore be typing up my new resume this afternoon. So thank you for that yet again, Frank. I'm just going to share my screen for a second. Can you see my screen? Can we see my screen? Mark, can you see my screen? Is that okay?
Yeah, we can see it.
Yeah, lovely. And you can all hear me. You can still see me and hear me. Excellent. Okay. Yeah, so I just wanted to introduce myself. Yeah, I'm Richard Lancaster. I'm the Bioresources Director at Atkins. Atkins is a strategic advisory and technical engineering and project management consultancy. And we are prevalent across the globe, as you can see from the picture on this presentation slide, around 50,000 employees across 50 countries. And this is the kind of the work that we like to be involved in, and to have been invited to this conference is a great honour. So I really appreciate the invite. Again, I think there's been some fantastic presentations. Mark has very kindly introduced the panel, so I won't go through that again. What we were talking about today is obviously biosolids is now seen as a resource, and I've been very fortunate in my career with being in the industry for over 30 years to have had the opportunity to play a significant influencing role in changing that from it being formerly, particularly in the UK, being seen as a waste. It used to just be an arrow that pointed out to the wastewater treatment process. Now it's obviously a really, really important part of the circular economy. The UK's net zero carbon ambitions, so it's becoming even more and more prevalent, which I'm absolutely over the moon about. And as you can see there, we've got some fabulous speakers. There's going to be a mixture of thought provocation. There's going to be a few people who are going to be doing a few slides. So there's a bit of a mixture in this next panel session, but hopefully we'll get plenty of time to capture people's thoughts and questions. I intend to do a few slides to start with to set the scene. Hopefully that will be okay, and again we'll hopefully stimulate some conversation and some input. Okay, so biosolids management. I thought I'd start with this slide because I think it's really obvious to us all now that biosolids is a resource, but I guess the reality of the matter is that this stuff is not going away. More and more and more of this is being produced. So as we improve wastewater treatment connectivity, as we improve the standard of treatment, we tend to produce more sludge, okay, of different times. The higher the standard of living, the greater per capita production that we see. And it varies across the world depending on people's quality of life, but the more sludge we produce. The greater connectivity to the sewer network, the more sludge we produce. The population increases, lifespan increases, the more sludge we produce. There's a theme here, as you can start to pick up. The converse to that is, before it started to be seen as an opportunity, the next part of these points were clear. As urbanisation increases, the potential for pollution increases, and sludge is a big part of that. Sewer sludge is a mixture of a lot of wonderful things, but it also has pollutants in it, so it has to be managed appropriately for it to be returned into the environment. And Chris and others have picked up on this throughout the slides. If it's managed poorly, it's costly, it increases emissions, it has a social impact. The climate change impact it can have is significant, and it can pollute the environment. So I think it's really clear to us all that there's a lot of this stuff. We're getting more of it, and we've got to manage it to absolutely get the maximum benefits out of it, but mitigate the potential for it to be a pollutant as well. So I guess my question for this group, and as we go through this, is this a never-ending problem, or is this an increasing opportunity? And I guess that depends where you are in the world and your maturity as an industry in that part of the world. So biosolids, why do we need a strategy? Well, we're producing massive amounts of this. I mean, I come from the UK and I thought we produced a lot, but when you start to look at the scale of some of the countries across the world, we don't. But I understand how much it costs us to manage biosolids in the UK, and I understand how much impact biosolids can have on the UK if treated poorly. I think the reality is that India is growing, as you can see there from predictions that it's going to outweigh China as the greatest population on the planet by 2027, and that really only means one thing, and that's we're going to have a lot more sludge to manage. And I see that as we've got a lot more opportunity rather than we've got a lot more of an issue. Just to put things into context, if it's managed poorly or averagely, it can be a hugely cost impacting part of the wastewater treatment process. We've talked a lot about resource recovery here, and there was a couple of people who mentioned cost saving as well. I think in its first instance, this can be up to 50% of the cost. In the UK, it costs about £300 million a year to manage biosolids and about £3 billion worth of capital and operational input every 5 years. These are big numbers, and the UK is a small blob on the screen at the top. And in terms of carbon, it has an emission, it causes emissions. And again, if poorly treated, I mean, it's the fourth largest emitter of greenhouse gases in the UK, 1% of the UK overall emissions, 50% of the wastewater treatment process or water treatment can be biosolids. So again, two big numbers there, 50% of the cost, 50% of the CO2 emissions. And yet, when I started my career, as I said earlier, this was just an arrow that pointed out to sludge, and it wasn't given a great deal of focus. And I'm really glad to say that that's changed for these reasons alone. So what would be quite easy to say is, I mean, biosolids has evolved, and this just proves the point. 1974 isn't when I started my career, although not a million miles away. It was just a waste. It's this waste that needs to be got rid of. And now we've transformed that from biosolids right away through to bioresources, where people recognize that this is a fantastic opportunity. People give us this for free, this product that we can get resources from. Isn't that kind of them? And what a wonderful opportunity that gives us. So I think I was just going to cover a few points here. So the evolving is we're beginning to think of this as a biosolid system, not as independent facilities as we've seen previously. It does lend itself to being treated as a system. I'll explain a little bit more about that later on. And that by treating it as a system, we can save millions of pounds in operating costs and in capital costs in building. We can go from simple recovery of water and nutrients by direct application right the way through the energy piece to resource, where we've seen lots and lots of great work that people are doing across the world at the moment around capturing these resources. And if there's a market and there's a regulatory framework, absolutely fantastic. If there isn't, that's the first piece that needs to be considered. So we've seen that evolution from the good old days of night soil in the UK and in lots of other countries where it's not connected to anything and it goes directly to the environment. And as I said before, as we start to work through this process, we start to see the growing complexity. And with that growing complexity, we start to think about, what does that mean for our people? What does that mean for the impact in cost? What does that mean for the impact in getting things wrong? What IT technology do we need to support? So the simplest form is the one there where we've connected to what we're calling a biorefinery, because this isn't a new term, and we start to directly recover some of the energy and directly cover some of the nutrients to agriculture. And then there's the opportunity of mixing organic waste. In the UK, that doesn't tend to happen because of the regulatory framework, but in other countries it does. If it's organic and it can be digested, it can be eaten in the big digestion stomach, then absolutely, why wouldn't you mix those? Because you can get some benefits from doing that. And then more recently, we've started to see a real focus in the energy, not just in terms of energy production, but use smarter, use less, generate more. So a real focus on energy and biogas and biofuels and fuel cells and hydrogen, and we've got a hydrogen economy growing in the UK now. And that can be used for domestic, industrial. It can be used in the process itself, as Miguel mentioned earlier on, and it can be used in transport. And obviously, a lot of these facilities have got biosolids or even sewage being transported to them, into them, and out of them. And therefore, there's an opportunity there. And then again, more recently, we've seen some of the stuff that we right at the start of this session with the initial 2 keynote speakers. There's lots of stuff in this. I mean, cellulose, alginates, so we can plastic packaging, bioplastics, paper, asphalt. So again, even down as simple as capturing the ammonia for things like fuel cells and fertilizer. So already we're beginning to see this picture change from we've got people bringing stuff straight out to agriculture and applying it right the way through now to the complexities of this process, as you can see there. And with this complexity, you start to need to think about what is it that I'm actually trying to achieve and what are my drivers for achieving that. And we've also now started, Dr. Fabi will, I'm sure, talk about later on about reducing sludge production. And if you're in Frank's world, and I added this during Frank's presentation because I thought it was pertinent to do so, no sludge, zero sludge. So thanks for that, Frank. So we can wipe clean this sheet and not have any sludge produced at all, and just lots of energy. So the world has definitely changed since I started in this industry. So defining a biosolid strategy, as I've mentioned, there's a lot of different ways we can go. There's lots of different technologies. I guess it's getting the right combination of those technologies and strategies to ensure that it's fit for purpose for the environment in which you live now and in the environment in which you may well be living in the future. So do we have the right people, the regulatory balance? Is it cost effective? Is there a market, being a really key one? And what are the potential risks and so on? So if I was thinking about that from a strategic planning perspective, I would be thinking, so situational awareness. What's my current system? Now, before I do anything, I mean, we talked, I think Chris mentioned earlier on, 5 years in the making his strategy, if not longer. So my view is always, what's your current system's capability and how can we absolutely make it the best it can possibly be with no regrets intervention? So what I mean by that is, can we do ways of working changes or capital interventions that ensure that we are on the right track, but we're not waiting for this wonderful thing to happen at some point? And what's the ambition in that changing environment? What are your drivers for change? We mentioned drivers in the last couple of presentations about dewatering and about waste management. So what are your drivers? And they're all different depending on which country you live in. We've got very different drivers. We mentioned fertilizers in some, power in others. Some countries, the power isn't a big issue. The costs for power aren't a big issue. So what is the driver? And we need to understand what that looks like in both the short, medium and long term. Future scenarios. So what could it look like? How do we know? What have we mapped? How have we determined what the future might look like? How do we set a strategy that gets us ready for now, but also mitigates the future environments that we might end up in? And then how do we get there? These are the really important questions now. So I've gone all the way around this circle and I've only just started thinking about the technologies at this back end. So first I've got to set what it is I'm trying to achieve, where I think I'm actually ultimately going and my ambition before I even start thinking about the configuration of technologies that I want to use, the gift I have of all those wonderful technologies we've just talked about and how best they align to my strategy. And then we're into how do we execute that? And this piece is incredibly important and gets missed quite often. That's all very exciting, but if you don't know how to implement it into your organization, into your environment, the likelihood is it won't stick. And then soon enough, you'll be coming back out saying, well, that wasn't very good. It didn't work, did it? And the reality is that isn't the case at all. It's about making sure that your business is operationally ready to receive this technology, this change in direction, this change in strategy, this behavioral change I think we heard on earlier on, and the stakeholder relationships, both within your organization and externally to your organization, as Chris mentioned earlier on. And I guess that leads me nicely to, that's really good, but how do you actually deploy it? So systems operator is something that I've developed through my time in the industry. And I think what's really important is to have exactly what operational requirements you need. You want high availability for an efficient and effective system. Treat it as a system. It is a system. Biosolids lends itself to being a system. But if you don't understand your system from end to end and where you can get the absolute maximum benefits and availability from that system, then you are always going to start to lose costs. So then you start looking at systems operations. How do you work as a system? How do you manage that as an individual system rather than who shouts loudest gets the most sludge, or where does the next £10 get spent to maintain those assets? This is when you need to really start to think, keep the system's performance high and the value will be high. Production planning obviously comes into that, and maximizing the most cost-effective end-to-end system utilization is absolutely critical to a well-operated strategy. And then finally, modeling it as a system. So system-wide understanding of where to invest in my asset base, where to put that technology, not just geographically, but where to put it and how do you configure it to my other facilities. This is ultimately important. And we mentioned dewatering before, and dewatering and removing the water from the biosolids is absolutely critical in this process to ensure that you give yourself the maximum opportunity. So hopefully that's given some people some food for thought. I'm going to now pass over to Pedro. So I'll stop sharing, and I'll just leave that up for a second while I do that. I'll stop sharing and I'll hand over to Pedro. So thank you very much. Pedro is the founder and managing director of P-Water. And I think, Pedro, you've got a couple of slides you'd like to present.
Yes, hello. Thank you, Richard, for a fantastic briefing. And I want to thank, of course, to Mark and to WWI the possibility to be here. It's quite difficult to to present something challenging and innovative after such presentations, and therefore I would also like to highlight and congratulate the quality of the session, previous session, and your introduction, Richard. I will just resume some thoughts on this. My key messages are basically 4 key messages. The first key message is basically, as we see before, we don't have technology issues right now. Wastewater, we cannot speak only about biosolids. We need to always think about wastewater and biosolids. We cannot think them separately, and we need to think that this is not a technology problem. Right now, from water and from wastewater, we have all the things the panelists said before: energy, bioenergy, biosolids, bioplastics, and last but not least, we can also make beer from wastewater. And that's the key message. We can do everything from wastewater. So this is one of the first message I want to present. This is a case from Portugal, Lisbon, a local wastewater company, one of the largest in Portugal, in Europe, wastewater, which is Águas do Tejo Atlântico. And basically they use this concept of beer, in English means turn the minds for promoting water reuse. And this is the kind of approach that could be interesting for developing new business models, as shown before from the DC Water, when putting and engaging the local community. Therefore, the second key message is basically COVID opens and basically opens a new era. Before COVID, of course, neutral and sustainability was always important, but now I think the high level is more open to sustainability and more focused on what we can do better. And new terms are being put on the table. A new term is born, which is called regenerative systems. From a water perspective professional, I think now it's also time for water being treated as also a central point. Water is related with energy, with land, with food, with health. And I would give 2 examples on this. One is this fantastic document made by European Forest Institute, where it looks for a circular economy for a holistic perspective. So this will be my third message. It's very important first to look at a holistic perspective, from the bioproducts, the urban perspective, the industrial perspective, the renewables, the energy. But at least, but not less important, is it's always about the local. There is no solution fits for all. You always need to think about local and how you can combine all the situations. It does not make any sense to produce a lot of biomethane to inject in the grid or to put in cars, in mobility, if you don't have a lot of people driving cars. It does not make any sense to produce a lot of heat if you don't have industrial symbiosis nearby. It does not have to do, it always local. So this is the third message. And the fourth message made by an example, the World Economic Forum has a very interesting tool where in terms of circularity, it highlights the regenerative systems. And it's important to highlight the possibility and the new business models. The forest will have a role in the next years, linking the biomass, linking the CO2. I think the biosolids related to forest are key issue, because of the soil, the structure. The industrial symbiosis, already some good examples in Denmark, and also very important to highlight and to think about wastewater and biosolids in a holistic perspective. Do you have agriculture nearby your wastewater treatment plant or not? Should I burn the sludge for producing energy? Should I have energy production to grid injection, or should I produce biogas and then biomethane for grid injection? These are all things you need to look at holistic perspective. Also, for instance, the district heating. Water is very interesting perspective in terms of heat, because it has specific properties. Also, water and wastewater sector could be very, very interesting to be introduced in a smart grid concept, using water and urban water utility infrastructures as real-time batteries. Also, digitalization is becoming more and more common, and of course, the blockchain and trading, and like the sludge Uber or the biosolids Uber is becoming more and more frequent. There is a top-level example in France where they combine the producers with the energy producers with the biosolids. Very, very interesting. And bioplastics. Also, there is a very interesting thing about the bioplastics, because as we all know, plastics and the problems of microplastics already in the water cycle are basically cumulative and persistent. So we need to think about different materials, different strategies. And basically, these are my 5 minutes slots, and thank you all.
Thank you, Pedro. What we'll do, I'm conscious of time, so without further ado, I'd like to, Chris, is there anything else that you would like to reflect on that you've seen so far, or have you got some more slides that you'd like to talk through, or is there a particular point that you would like to raise before I move on to the next panelist?
Yeah, if you don't mind, I would like to just make a couple points. I don't have any slides, but I've heard some really interesting phrasing, and you, Richard, used a couple of terms that are near and dear to my heart that I want to, you said we need to evolve, and you referred to the digesters as a stomach. And I use that analogy all the time. And I really think that we are starting to treat biosolids as an asset and not a liability. And as Frank pointed out, we use 100-year-old technology in our wastewater treatment plants because it works, right? Hang on a second. Yeah, so we're using 100-year-old technology because it works, and we are really our primary objective is to keep pollutants out of our receiving water. That's what we want to do. But I truly believe that biosolids can be a catalyst for change and evolution in our sector. I ask for money to do projects all the time, and the mantra of our CFO and our finance department is, well, we don't take risks with ratepayer money, which I get, right? They're trying to protect the ratepayers, and therefore we end up using 100-year-old technology because it works. And then the other mantra is, well, that's not our core mission. You know, putting up solar panels or recovering heat from the sewers isn't our core mission, and we don't have money to do that. So again, we're not going to take risks with ratepayer money. But for us, I think in DC we've sort of turned the corner on that, and I'm really proud of our board for funding the Canby thermal hydrolysis and digester project, because it is proving that we can generate revenue from our biosolids. You know, we're making electricity, which we're using. That translates to savings, but I'm selling I sold $1.1 million worth of renewable energy credits from that. And we're selling the biosolids, $500,000 worth of revenue. And guess what? That is non-ratepayer revenue. That is not money that is coming from our ratepayers. So our CFO is more willing to take risks with stuff like that. So, you know, we're going to fund things like sewer heat recovery, because there's an enormous amount of heat, thermal energy in our sewers that just gets pumped out into the rivers. And I do believe that you know, if you think of the city as an organism, and you referred to this already, Richard, but the stomach, or the digester is like the stomach for the city. And I read a book a couple of years ago by Michael Pollan, American author, writes a lot of books on food. He wrote one called Cooked, and this is a fairly widely accepted concept that, you know, human evolution had something to do with the fact that humans discovered fire and started cooking their meat. And when you cook the meat, the proteins are much easier to digest. So it took less energy in our stomachs, and our stomachs were able to shrink. And then our energy was able to use elsewhere in our body, and our brains grew. And it's one of many theories, but I think it's good. And I think that it is an apt analogy for us, because the stomach in our city, we all use digesters, these gigantic digesters. But when we put thermal hydrolysis ahead of it, we hydrolyze the biosolids. It becomes much easier to mix. We can feed it in at 10% solids, and we can shrink the size of our stomach. We shrink it down. Instead of 8 digesters, we need 4 digesters. And it's saving us a whole bunch of money, and therefore we have money to do other things, and we can evolve in a really a better direction because we have this available cash. So I really just think that biosolids can be this catalyst for change and for innovation, but it's only going to happen if we treat it like an asset.
Absolutely. Thank you, Chris. Some brilliant points there. And I guess just to add from the UK experience, yeah, I use very similar things. Cooking your food before you eat it is essentially what advanced digestion processes are there to do, and it does absolutely take it to a different level. And I guess the catch-up piece now is, how do we convert more of that biogas to energy? Is the key. It's the next part of unlocking that key. But you know, from the UK perspective, I've seen us go from predominantly incineration strategy, because it was the right thing to do at the time, and now we're 100% recycling in the UK, and the predominance of that is advanced digestion, which is, you know, is absolutely fantastic. And the UK make about £5 million a year from selling biosolids as agricultural fertiliser. That's only 2 companies. That's not all 10. And about £60 million worth of energy is produced from the UK water industry, which otherwise would have been bill payers' money. So, you know, and at this moment in time, the market isn't as prevalent as it should be with other resources. And we mentioned some of the stuff that Frank talked about earlier on, and others around recovering these other valuable resources. And that's the part of the biosolids world which is really changing now in the UK, and they're recognising that. And I guess countries like India have got a fabulous opportunity to step over all of that learning and go straight to the end game, I guess, where a number of us already are, Chris, which is brilliant, isn't it? And that's the opportunity here for people else across the world who aren't at the same level as yourselves are in DC, and they are in UK and in Europe. So sharing that knowledge to enhance other people's capacity is a fabulous gift.
Yeah, as we've seen today, I think we're only scratching the surface.
Okay. Any other points, Chris, before I move on to Malcolm?
Nope. Thanks again.
Brilliant. Thank you very much. Okay, Malcolm. Malcolm Fabi is the Chief Operating Officer of Drylet in the USA. I've had the pleasure of presenting with Malcolm before, and I'm sure you'll enjoy listening to Malcolm. And Malcolm, I'm assuming you've got a couple of slides that you'd like to share with us?
I do. I'm sharing them now. Can you actually see my slides?
I can see them now. Thank you, Malcolm. Yeah.
Okay. All right. So thanks for the invitation. I think this is an incredible panel. It's always great listening to all of the interesting speakers that have spoken today and learning about all the incredible things being done. So the topic we're looking at right now, which is this biorefinery concept, is, if we think about where wastewater treatment has come from, we started out about over 100 years ago, only and mainly focused on wastewater treatment, removing carbon from water and essentially doing nothing than trying to meet regulatory requirements. And then in the mid-1990s to the early 2000s, that focus shifted. Regulatory requirements now went to nutrient removal. And one of the things we began to find was that the cost of removing nutrients was in many cases almost as much as the cost of removing all of the carbon. And it began to make sense for us to start thinking about reclamation. The wastewater plant has a reclamation system, recovering, rather than just letting the nutrients go out, recovering it. But what we've made from the 1990s till now, what we've mainly been able to do is essentially focus on the recovery mostly of energy. Energy is a lot easier to recover. You take the biosolids, you break it down in a digester, and the immediate thing that comes out is biogas. In the biorefinery concept, we're going further than that. We're starting to say to ourselves, that thing that has eluded us, which is cost competitive, economically viable ways of removing all the resources available in biosolids. How do we make that happen? If you look at the picture to the bottom, the heart of the biorefinery concept, the heart of biosolids utilization is the digester. If we take those biosolids, if we rip them apart, split them open, inside of that bacterial cell, inside of that primary sludge going to the biodigester is carbon, is nitrogen, is phosphorus. We can convert the carbon to biogas, but what do we do with the nitrogen and the phosphorus? Well, we can recover the nitrogen and the phosphorus. It can become a fertilizer. We can actually take the methane coming out, and rather than just using it for energy, it can actually be converted into a bioplastic. And beyond just converting biosolids in the plant, the digesters in most wastewater plants has enough capacity to actually take about 2, 3, sometimes even 4 times the amount of organic load it is using. So we could actually go to households. We could get household waste, food waste from households. We could get food waste, fat oils and grease from industry. We can go to agricultural producers and take the manure and turn that wastewater plant into a biorefinery, but the heart of it is the digester. Now, in my view, there are 6 challenges that we have to address. The first one is that the most efficient digesters will give you, without pretreatment, will give you no more than 40 to 50% recovery of volatile solids. So only a 40 to 50% recovery. And this is a digester that has about a 20-day retention time. So the fundamental question is, how do we boost lysis to recover more nutrients? The second one is, how do we enhance the efficiency and the cost of digestion? Right now, it is not economical to construct a digester for most wastewater plants that are smaller than 10,000 cubic meters a day. The US, for example, has 15,000 wastewater plants. We have only 1,500 of those plants with digesters. So only 10% of the wastewater plants in the US have digesters. And so how do we make the digestion process more economical? The reason why they don't have it is it's not economical. The third one is, how do we improve the economic viability of nutrient recovery? We've had algae removal has been around for over 20 years. Struvite recovery has been around for over 20 years. Yet, despite the fact that these technologies exist, we've not been able to turn them into things that are viable enough for us to have in everyday plants. The fourth point is that I'll use the US as an example again. We have 1,500 wastewater plants with digesters, which is basically 10% of the total. And of that 10%, 1,500, only 300 of them use their biogas. The rest flare it. So why do you have biogas when you can't use it? The reason why they can't use it is it is not viable. It is cheaper for them to get energy off the grid than to try to generate energy from their biogas. So if we can't convert all the biogas to energy, could we think about other uses of methane, for example? Things like methanotropy, where we can actually take the methane and the CO2 and convert them into into other materials, into bioplastics, for example, into methanol that we can use in other parts of the wastewater treatment process. And then 5 and 6 is about business models. We need to become more innovative, not in the area of technology. I completely agree with Pedro in that fact. Thermal hydrolysis has been around for 20 to 30 years. Nothing has changed in that technology. But now we're starting to adopt it. Why? Because we're starting to see different ways in which we can innovate our business models that allow us not to be wholly dependent on policy, but to have economically viable ways of making things happen with the technology that we have and the recovery models that we're looking at. And then the fourth one is, the final one, the sixth one is partnerships. We need innovative partnerships. I like what Chris was saying, you know, when Chris was describing what they were doing in DC, and I happen to actually live in DC, it took partnerships. You have to find partners. They might be private sector partners, they might be governmental partners, they might be not-for-profits, but you need partners that can take these innovations and they can take these products and utilize them. We need partnerships. A wastewater plant, if you are truly a refinery, then part of what you need to do is to find users of your raw materials. So in the same way that a refinery is linked with somebody producing oil, we need to be the oil producers for somebody downstream that is going to utilize those products. And I'm glad to see that there are companies like Mango Materials, Calista, Unibio that are actually starting to do that. So the heart again of the biorefinery process is the lysis process. Anaerobic digestion is 4 stages. The critical one, the one we have the most problems with, is hydrolysis. How do we convert, how do we take 50% volatile sludge reduction, which is really limiting? How do we make that higher? How do we get more out of a digester? Right now, there are different ways we do it. It can be thermal hydrolysis, it can be shear pressure, it can be chemicals, it can be ultrasound. All those approaches would require some type of resources. And in many cases, that is actually the hurdle that a lot of people find difficult to overcome, just the cost of these additional pieces of equipment. But one of the things that we're looking at, like companies like ours, is bioaugmentation. Fundamentally, we're using microbes in these digesters. Can we tweak those microbes? Can we enhance them? Can we make them do more in a given footprint? And so what we focus on in Drylet and other companies like we do is basically taking these microbes that enhance the digestion process, and finding innovative ways of introducing the microbes, making them viable, protecting them, and ensuring that they can actually help us boost the lysis process. If you boost lysis, you boost the outcomes from the digestion process, and the outcomes from the digestion process are actually the raw materials. The biogas is a raw material, and then the nutrients, the nitrogen and the phosphorus that is increased when we boost lysis, that also can then be utilized for whatever downstream utilization, whether it's nutrient recovery, whether it's algae production, or other things that we might want to use it for. This stuff is real. It's actually been done in the field. This is just an example of some work that we've been able to do with bioaugmentation in a 200 million liter a day plant, about 200,000 cubic meters a day, where you're able to take biogas from about 30,000 cubic meters a day, boost it to 40,000 cubic meters a day without capital equipment, where all you're doing is you're looking at the microbes and you're finding ways to enhance what is going on with microbiology. So I will finish with this slide again, reminding, and my position is fundamentally this, that the technologies we need are here. Yes, maybe some of them might need some tweaking, but the fundamental challenge that I believe we have is the challenge of the economics of the process. And we need to find partners, we need to come up with innovative business models that overcome those hurdles if we are to see this become real, if we're to see this become widespread. And, you know, I look forward to the conversations that we're going to have in terms of being able to flesh this out in more detail. Thanks.
Mr. Fabi, thank you very much. Some great thoughts again. Innovative partnerships, I think, is absolutely critical. I couldn't agree more. I think partnering with each other is really important. I think the water industry, in my understanding, has always had this desire to try and solve the problem themselves rather than innovate and share and partner with others to do that. So the other bits I heard there was bioaugmentation, getting more conversion to energy from biosolids. I'm conscious of time. I'm going to move on, hopefully, to my my last panelist, who's a technical director of Canby, and you know, this guy has got a lot of papers out there. He's done a lot of conferences, and I've known him for a very long time. And hopefully, he's on the line and able to give his thoughts. I don't know if you've got some slides you want to talk through, Bill.
Hi, Rick. Yes, I do. I'll just okay. So a lot of what has been discussed today, I'm going to touch on. Really, my presentation today is going to be a bit more high level than we've just had. More, you know, to provoke some thoughts, some ideas. Let's have a look. You see my slides now? Okay, so yeah. So really, when we are here, and I'd like to thank the organisers for the opportunity to present and to be part of this discussion. Typically, when we look at innovation, the issue we have in our industry, it's a fundamentally conservative industry. So, you know, we have a lot of conservatism. There's a lot of risk associated with taking chances. Engineers hide behind textbooks, which have been written many decades ago. And that stifles innovation. So typically what you see is there's a race to be innovative, but the race is for second place. No one wants to be first. No one wants someone else to be first and take the chance and take the risk and learn from that experience. So you need trailblazers in our industry. And we saw the example of Washington, D.C. You know, thermal hydrolysis had been around for many, many years in Europe, but not in the US. And as soon as Washington, D.C. took that leap of faith that you need to take, that opened up a whole industry in the North America for thermal hydrolysis. There are now, you know, 10 facilities on the back of the story that DC Water have taken. So when we look at innovation at the moment, it's kind of most of it is limited by how we can do things better. You know, how can we improve primary settlements to get more carbon into our digesters? How can we improve activated sludge treatment by doing deammonification or something like that? How can we improve biogas production? A lot of these improvements, however, the issue with these improvements is we're improving something that is, as we've heard already today, we're improving something that is fundamentally old-fashioned. So instead of asking the question, how do we do things better, should we ask perhaps also the question is, why do we do things the way we do them? If we look at a typical wastewater treatment plant today, primary treatment, digestion, dewatering, nutrient recovery, and struvite recovery, all of these technologies are from the 1800s. All of these technologies were built and designed in a bygone era for drivers of that time. You know, Victorian engineers, they weren't particularly concerned about energy recovery or nutrient recovery or even carbon footprint. They were concerned with health issues. They had different drivers. So they built a lot of technology, which was low risk technology with a long life cycle, a long lifetime. Anaerobic digesters are built for many, many years, you know, not just for 5 years. These are 70, 80 years some of this infrastructure is around for. So you have a lot of technology which was built for previous drivers. Subsequently, what that means is a lot of that technology is inherently inefficient with respect to nutrient recovery, inefficient with respect to water recovery, inefficient with respect to energy recovery. Of the things needed to sustain mankind on Earth, water, phosphorus, nitrogen, energy, raw elements, rare elements, a lot of these things are passing through wastewater treatment, but the treatment plants we have today are intentionally designed on the whole to destroy these materials. We look at activated sludge treatment, as Frank mentioned earlier, we are using a lot of energy to intentionally destroy nutrients. And then we're using a lot of energy in the Haber-Bosch process to put those nutrients back in the wastewater system. So we really need to think about what we are doing in that respect. So that arguably the last true paradigm shift in our industry was the activated sludge treatment. Everything we've seen really since then is improvements on existing systems. But we've heard today about things like the algae and as in Malcolm's presentation, these are the next paradigm shift that we see. A lot of innovation we see is just an improvements on a system which is out of date. You know, people have mentioned this today somewhat, but really, if we're talking about sustainability, we are living today in a climate emergency, I would say. The sustainability of mankind on Earth is diminishing day by day. So if we're looking at sustainable solutions, these are solutions which have to be ones which reduce the carbon impact, the anthropogenic carbon impact of mankind on Earth. Every time you put the news on, you see record droughts, record storms, more frequent flooding. Technology of tomorrow has to accommodate all of these things. We're seeing all these record fires in Australia, the smoke from which you can see in South America. As I said, the issue we have in our industry is a lot of the technology has a long life cycle. So anything you install today, by and large, is going to be in the ground in 2035, in 2050, when we're looking at all these carbon targets. Work that I've done before, looking at the timing of infrastructure development is key. So, for example, if I have a new technology I want to put in, and I delay that by, say, 5 years, just by talking about it, the accumulated carbon emissions in those 5 years will take multiple decades to reduce, even when I put my new technology in. So timing is of the essence. So anything we do really has to be done yesterday, in my opinion. So looking at sludge production, if we look at the world, the population of the world is going up by about 1 billion people every 12 to 13 years. Currently stands at about 7.8 billion people. So what we're going to see with increased populations, increased sludge production. We are seeing more urbanization around the world. We're seeing megacities. We are seeing a lot of investment in Far East Asia, where a lot of technology and infrastructure is being installed. So we're going to see a huge increase in sludge production, especially in Far East Asia. Latin America, we're going to see a big increase in sludge production, less so in Europe and in the United States. But in India, we'll see a lot of sludge increase. So if we look at that sludge production, that is not only is it going to increase in production, but it's going to change in composition. So now it becomes a question of regulations. So as we've seen, sludge has evolved over the years with primary settlement. Before activated sludge treatment was invented, primary sludge digests and is very amenable to further processing. As the wastewater regulations get tighter, more and more waste activated sludge gets produced. And we've heard already, waste activated sludge is the limiting step for treatment. So we need to look at these things in combination, as we've already heard today. So if we look at the amount of sludge we have, I'm going to put some high level numbers here. This is what we currently do. So 1 ton of dry sludge has a calorific value of around about 7,000 kilowatt hours, which in terms of oil equivalents is about 0.6 tons of oil equivalents. If we digest that, we'll get somewhere around about maybe between 3,000 and 4,500 kilowatt hours of energy in a biogas, or up to 270 cubic meters of biomethane, which we can then put into vehicles. And then we have nitrogen and phosphorus. Actually, the trace metals and nutrients are much more valuable than the nitrogen and phosphorus. I think we don't look at them as much because they're harder to quantify. But as we've seen today, these are the products we recover now because that's the limitation of the technology we have. Going forward into the future, should we be recovering different materials? If we look at biogas from a purely financial perspective, the value of the biogas is probably 10 times less than the value of the volatile fatty acids that we've destroyed to convert the biogas. So we need to look at it from a financial perspective as well. So really, I'd like to finish that, we have an existing technology at the moment, which we need to optimize. We need to do something different. We need to make it perform in a way for which it was not designed. And that will help us in the short to intermediate future. Longer term, there may be a different solution altogether. But the biorefineries concept is definitely taking us a step into the future, into the 21st century, to meet 21st century drivers, rather than the 19th century drivers, which most of our technology has been designed for. So, as I said, we need trailblazers. We need people to take chance and risk. This is becoming more urgent day to day. And it's a combination of speaking with the right people, developing the right relationships, and it has to be environmentally sustainable with respect to carbon footprint, but also with respect to economic impact, because unfortunately economics control a lot of what we do, and it has to be economically viable as well. So with that, I'd like to hand back to Rick and have a discussion. Thank you.
Thank you very much, Bill. Really thought-provoking stuff from all of the panelists. Unfortunately, we are significantly behind schedule. Nothing to do with the last panel group, clearly. Some concise reports back from you guys. Well done. You all kept to time brilliantly. Okay, so there are a couple of technical questions for you, Bill, and others, and we'll make sure that you get those so you've got the opportunity to answer them. Forgive me, the people who put those questions in, but unfortunately, as I said, we're struggling with time. I think the points I'd like to clear up here are, Bill was saying we've got to have solutions for the time that we're in. I couldn't agree more. Coming from Manchester, where the great innovation came from, and knowing how old-fashioned we can be down there, it's great. It's great to hear what the world thinks of our amazing invention and how it's still pertinent today. We heard about bioaugmentation. Can we get more and more from what we've got, and partnerships? And I thought that was fantastic. Chris's stomach of the city. I love that. I think that's the reality of where we are at this time, and how important it is that you put the right things in your stomach to make sure that you're not ill, and that's sustainable. And I think the one that excites me the most, because I'm a Northern English bloke, is the turning it into beer. And I absolutely love that concept, and I need to know more about that immediately. So I'm going to hand now to the CEO of Smart Water and Waste World in India for their closing remarks on the conference. Thank you all very much for your participation, and for those who've took the time to listen and are still listening now. Thank you.
Thank you, Richard. What a wonderful panel discussion, and what a wonderful way to end a 5-day knowledge series that we had conceptualized at Smart Water and Waste World. I would like to thank Mark. For the past 2 days, he's been moderating the session, and he's put this wonderful lineup of speakers for us for an important topic that we all believe in India, wastewater and then sludge management. As Mark shared in his session, he is heading WEX Global, one of the largest or biggest event gathering of water utility leaders across the globe. And we are working very closely with Mark to see how we can bring WEX Global to India. And, we are excited to maybe meet all of these people whom we have heard online today in person very soon. This brings us to the end of a 5-day India Water Innovation Week. We had conceptualized this event as a platform where we could try to bring experts across the globe to practitioners out here in India and also across the globe. As Mark shared with you at the start, we had close to around 4,000 people who have attended over the last 5 days, and we had close to 50 speakers from across 17 countries. So I would like to thank all of our partners and supporters, WEX Global, Mark, IDA, SWAN, and all the speakers over the 5 days who have worked tirelessly for this event. I would like to thank all of the attendees who have taken time out of their busy schedules for 5 days to listen to these particular sessions. And finally, I would like to thank my Smart Water and Waste World team who have been working behind scenes, in helping this event become a success. With that, I would like to bring an end to India Water Innovation Week. I request you to take some time out to fill the poll that we have, put up for you. And with that, and thanking all the speakers, I bring India Water Innovation Week to an end. Thank you all.